Here we are. It's the physics video lecture once again. Physics 2A video lecture 35. We are beginning a new chapter. Thermal physics is what it's called. And let's go ahead and write this down. Chapter 10, thermal physics. And it just begins. It's a new branch of physics, so to speak. It'll tie into everything we've done, though, very nicely. But it just begins with hot and cold. Okay. So thermal physics begins with the sensation of hot and cold, and we take it from there. So sensation, hot, cold, and we associate that, that's hot. Sensation, hot and cold, we associate that with a flame. Brought one to class right here, and say ice. So that's just the sensation, or hot water, cold water, and so forth. There are phenomena, that's the next thing we mentioned, that go along with this. And the one we're after, I have a nice demonstration of right here. So these are two brass objects. There's a ball and a ring, and the tolerance is pretty close. The ball will not fit through the ring, but it's close. So I'm going to apply some heat to this because I brought my flame with me. And there's no doubting the sensation. This thing is real, okay? It's hot. So it's going to take a minute or two to heat soak this thing. And as it's happening, you don't see anything changing about it. Maybe if you do it a while, it'll start glowing red. It is heating up. I wouldn't want to touch it now. It has expanded. Okay, the ball passes through the ring now. Passes through. Okay, so what we have is what's called thermal expansion. So the first of these phenomena is, and I'll go ahead and draw it for you. We have the demonstration. We have the ball right here, and on another handle we have the ring, and this is thermal expansion. Thermal expansion. Now, a second phenomenon is with this strip of metal here, more or less straight, okay? This strip of metal, all I see is a slightly different color from one side to the other, okay? But what we're going to see is that it bends when we apply heat to it. It's rather pronounced. And the explanation here is that these two colors exist because there are two very thin sheets, strips of metal that are bonded. This is called a bimetallic strip. One metal has a greater thermal expansion than the other, and it pushes it over the way we saw it bend there. So that's an example of thermal expansion as well. So this demonstration, we've got that strip, and you apply flame to it and it bends over like that. Maybe I'll do one of them dotted, okay? It bends over. This is called a bimetallic strip. You'll find these in old-fashioned thermostats, or if you have an oven thermometer, you open it up, you'll probably find a bimetallic strip inside, okay? Now, this gives us an idea. Since this was very hot, and this is room temperature, why don't we just put a scale here and call it a thermometer? So that's what we have. We now have from the sensation of hot and cold, we went to the phenomena, two different phenomena of thermal expansion, or two related phenomena of thermal expansion. And that leads us to, you love numbering things, 1, 2, that leads us to point 3, the construction of thermometers and temperature scales, which will allow us to objectively state something about these different sensations, because hot and cold could feel a little different to a different person, but if we get a device that does it accurately and a temperature scale, then we have something reproducible. So let's call this thermometers and temperature scales. So that's what follows from what we've done so far. Now, I brought a little thermometer here, and that is not going to be visible, but you've seen these before. There's a little reservoir of a fluid on the bottom, and if I just grab it, it'll go from room temperature to body temperature, and I can actually see the little column of fluid moving up here in real time. Okay, so what I could do is have a bucket full of ice water and put this thing in here, and then locate where the column arrives at. Let me draw 2 of these for you on the board, and we'll talk about these thermometers and temperature scales. Yeah, I just like to draw a version of this where there's my reservoir, there's my capillary, and I've got the red fluid in here. It's kind of an exaggeration, but it'll make our point. There's the reservoir, and then the fluid goes up in the capillary to a certain degree, certain point. I like to draw a second one right next to it, identical in all ways. Okay. And it has liquid inside, goes up somewhere as well. And if I did the bucket of ice water, say it would settle down to here, and I could say ice melts. If I heated this thing to boiling, and then column is higher here, so then I would have a point where water boils. And now it's just a convention how I decide to divide up my scale. I'm going to take these important ones here and label them 0 and 100. So I've just divided this up 100 times, and that's my Celsius scale. So Celsius, and if I divide them up a little finer, and for some reason I call ice melting at 32 and water boiling at 212, then that is my Fahrenheit scale. So what you see is that these conventions are arbitrary. Okay, we could divide it up any way we want and give it any numbers we want. But this is what's been done historically. So we've got these 2 temperature scales, Celsius and Fahrenheit. So what are we going to do with those? Well, you can look up and calculate conversions, no problem. I'm going to go ahead and derive the conversion formula right now, because it's a nice little linear algebra application. Good, so we have these temperature scales, and we want to convert from one to the other. So the Celsius, by the way, that's the one we're going to use in most of our physics formulations. And then the Kelvin, which comes in a little bit as well. The Fahrenheit is what we hear on the news, okay, and read in the paper, so we're familiar with this. Good, so let's call this conversion. And we can make an interesting graph here. So this is kind of fun. Okay, so we put our degrees Celsius and our degrees Fahrenheit here, and then if we go from 0 to 100 here, we might be going from 0 to 212 here and 32 there. Okay. But both thermometers are the same. The scales are just different names. So we have this point here and this point here, and these will be connected by a line. Okay. It's just a linear conversion between the one or the other. Okay, so what do we have here? We have, if you guys remember, the slope is the rise over the run, so we have 212 minus 32, that's 180. And then 100 minus 0 is 100. So that's 18/10, which is 9/5. So now we can use the point slope formula that you guys remember learning at some point in time. And here's our graph. We could say T degrees Fahrenheit is equal to 32 plus the slope, 9/5, T degrees Celsius. Okay, so that's 1. And if we want to solve for T Celsius, we can say T degrees Celsius is 5/9 times temperature degrees Fahrenheit minus 32. So you see, you can always have these at your disposal if you remember your point slope formula. Okay. So those are our conversion formulas. And I'm going to do, well, you know, I'm just going to assign this. You should leave room in your notes. So here, I've got room in my notes right here. Just for the record, what are some temperatures in Fahrenheit? Let's do this. So we've got degrees Fahrenheit and degrees Celsius. So we have 32 and 0, and we have 100 and 212. But what about, and we see what those are, what about room temperature? Room temperature, and how about body temperature? I'm going to put question marks here. You guys figure them out. So you know at least that, okay? Freezing, room temperature, body temperature, boiling. That's a good set of temperatures. Okay, so consider that homework, or if you have a moment while you're making your notes to figure that out and type it in. And room temperature, there's an official body temperature. It could vary a little, but room temperature may be the one you prefer. The one you prefer to have your room heated to. Okay, or cooled to, as the case may be. Now, I think, yes, I want to now discuss this device here. I'm just going to check our time. Good. So we have gone from our sensations to our thermal expansion to our temperature scales, and we have a conversion there just for good measure. Now I want to introduce this gas thermometer. This is a bit of a mock-up, but it'll do. It'll do. So first of all, let me show you what this is. There is a volume of air in here, okay, enclosed. Got a tube going to here, and then this little reservoir of a red liquid, and you can see it goes up to here a little bit. This curve goes up here, this curved tube, and this is just open to the air right here, so atmospheric pressure. And what I'm going to do is heat this. Maybe I'll get this guy out of the way. Heat this right now. You know, I could actually just hold the flask in my hand, and you'll see an effect, okay? Because the air, you can say, well, that's a body temperature thermometer, but I want to blast it with the flame just because I can, okay? That's a little more than we can do with body temperature. Without doing any damage here. Okay, and it comes back down again. So this is a gas thermometer. And it's not a constant volume gas thermometer, which is what I'm going to draw next, but it is a gas thermometer, and I'll show you the difference in the two in a moment. Okay, and the functioning here is that we have, that's a little bit warm to grab, but this works. So there's air inside, and then the air gets heated up to a certain temperature. And if you had this thermometer in, say you could boil water or freeze water, and then you'd know the exact temperature of the air in there. So that then will, by thermal expansion, increase the pressure on the fluid there, and that pushes it on up the curved tube. Good, so that's how the gas thermometer works. And let's go ahead and investigate it a bit more. Plastic got a little too hot, but there's no permanent damage done. Okay. Okay, so this here we're calling the constant volume gas thermometer. It's a bit different than what I'm showing you, but it plays an important role. So I'm going to go through with the whole discussion. Constant volume gas thermometer. It's really what we're looking at to a certain degree. So there's our beaker. And we could have and what do we have in here? We just have air in there. We're going to bring that over here to another, let's say like this, to another reservoir, and I'm going to complete my sketch before I label it. So now we have a flexible connection, which is what I don't have over here. And then we're going to go up to a column like this that's open to air. Okay. So here we have my red fluid. Okay. It's going up to here, and depending on the temperature, it's reaching a certain height. Okay. Now the constant volume refers to this volume right here. So this level of the fluid in here has to be maintained. Okay, we maintain this level, and we raise and lower this thing, and that allows us to keep the volume in here constant. Okay. In here we just have gas. Gas molecules in here, and this height of this column is very important because there is a pressure of the gas in here, and there is atmospheric pressure up here. So this will be P atmosphere. And what I'm going to label this difference between these two levels, we're going to call H. And you can think rho GH, right? There's just going to be a pressure difference between the atmosphere and the contents here in the gas. And yeah, so to complete this picture, I like to put a thermometer here, degrees Celsius. So that's our constant volume gas thermometer, and the pressure in here above atmosphere is indicated by the height of the column. So in fact, we could say, I'll just draw an arrow there, P equals P atmosphere plus rho GH. Good thing we studied fluids, right? That's your depth formula. And you have to keep the volume constant. That's important, and that's done by always maintaining this fluid level right there. Okay, good. So you've got your constant volume gas thermometer, and now you want to graph the pressure versus the temperature. So let's go ahead, and this is a pretty big graph. Pressure versus temperature in the, let's write the gas thermometer. Pressure versus temperature in the gas thermometer. And careful here, we got to leave a lot of room to the left. Okay, leave a whole lot of room to the left. There's temperature in degrees Celsius. There's pressure, you know, arbitrary units, could be atmospheres, doesn't matter. So, two good temperatures are 0 and 100 degrees Celsius, because we can have a continuous change of temperatures as we go from melting ice to boiling water. And then we measure those pressures and we get a line, or we get some data points that are increasing. Okay, you got a positive slope, and we do another gas, so that we evacuate this gas, which was just air, and maybe put in pure carbon dioxide, put in pure helium, hydrogen, nitrogen, and we get a different set of data points, like that. Okay, now what turns out to be the case, and this is just an experimentally verified thing, is that these two lines, they aim at the same point. And that is to say, they can be extrapolated to the same point right here. And if you do it with a third gas, and you guys make your lines better than mine, okay? I'm not going to redraw them. You do it with the third gas, you'd also extrapolate a straight line to this point here, and this is T equals negative 273 degrees Celsius. Okay. Maybe I will improve that line myself. Let's look at too bad. The thing to do is to draw the line first, right? So here's our point. There we go. Here's our blue one. And these were data points. So data on the right side, extrapolation on the left. Okay, but what then comes to mind is that, well, we have a nice straight line. Couldn't have known that, but it turns out to be the case. We have a straight line. And so if we chose this as our zero, if we chose this as our zero, we would just have a linear law for the pressure. So pressure versus temperature would be linear, but only if we choose this temperature scale where 0 begins down here. So that's why we call this 0 Kelvin. It doesn't get a little twiddle up there, it's just 0 Kelvin or 0 K Kelvin. And the significance, first of all, is that we just get this wonderful straight line law, okay? And because of this, we can then write T is proportional to T if T is measured in Kelvin, okay? Now the other significance is that this turns out to be absolute zero, the coldest that anything can get, okay? And to understand that requires the atomic hypothesis, because if the gas molecules in here come to a complete stop, they can't go any slower than that. They're frozen, they can't get any colder than that. So we're going to deal with that in a little while. It'll be called the kinetic theory of gases. But for now we have this empirical law, pressure proportional to temperature. So that's the significance of the constant volume gas thermometer. So I'm going to go ahead and write that down. You've got the picture, I'm going to erase. Well, now I've erased it. You can actually use a similar device and keep the temperature constant and vary the volume. And then you can actually get at the entire ideal gas law. Okay, so we now have, and let's make sure we hold on to that fact, we now have the Kelvin scale. And then we would say T in Kelvin is equal to temperature in degrees Celsius plus 273. So those are the two scales we use, the Celsius scale and the Kelvin scale. There will be a few places where we have to use the Kelvin scale. One of them is already the ideal gas law. Okay, good. Let me see how we're doing for time here. Fantastic. Okay, so we got the Kelvin scale. And again, if we use the Kelvin scale, then we've got pressure proportional to temperature for the ideal gas law. So we're going to return to the ideal gas law. I'll just put that as a note here since we talked about that. If T equals T Kelvin, then ideal gas law, we have pressure proportional to temperature for constant volume. We're not going to write the whole thing down until a little bit later. Okay, so far that's what we have. I want to return to the thermal expansion now. We have our temperature scales. So returning to thermal expansion, we've got a little more we can say about it. And first of all, what we saw was linear expansion. So the linear expansion law looks like this. If you have an object of length L, so object of length, I'll say length L sub 0, and then you apply temperature to it. Say this were a metal ruler and you could heat it up with a flame. Then the change in the length is going to be proportional to, there's a proportionality constant we're going to call alpha. It's going to be alpha L naught times delta temperature. So this is delta temperature in degrees Celsius. This is called the coefficient, the linear coefficient of expansion. So coefficient of thermal expansion And we always ask about the units, right? What are the units here? Well, we have length, so that'll be meters. We have a length, that'll be meters. We have degrees Celsius, so alpha must be 1 over degrees Celsius. So the units of alpha are 1 divided by degrees Celsius. And I think I have a numerical example here for us. So suppose this were a meter stick. How much would it expand if I say dropped it in boiling water? Well, for that we need to know alpha. I believe I've got an alpha here for us. Yeah, alpha for aluminum. Example. And by the way, you have this in your book, so you could write down, and you could leave some space in your notes and write down 2 or 3 of these of interest. So alpha sub aluminum is equal to 24 times 10 to the minus 6. That's probably straight out of our book. Okay. So suppose we want to find the temperature. Okay, now this is an aluminum rod. It's an aluminum meter stick, and there is its coefficient of linear expansion. So what temperature would make this 1 millimeter longer? What temperature would make it 1 millimeter longer? You know, I should write this thing out a little differently as well, just for the record. So I have this law here. We can also write the delta L as L minus L0, and then we got alpha L0 T minus T0. Okay, that's the same thing as this right here. So our example what temperature difference will make delta L equal 1 millimeter for a meter stick? Question mark. 1 millimeter, 1,000th of, that's something you can just barely see, but it's a good application here. So the delta L over L0 alpha, so we would say delta T, since that's what we're looking for, is delta L over L0 times alpha, and then we've got 10 to the minus 3 over 1, meters cancel, and then we have times 24 times 10 to the minus 6. So that will give us 1 over 24 times 10 to the 3. So it's 1,000 divided by 24. 1,000 divided by 25, whatever that is, 40. 25 times 5 is 100. 25 times 4. Divided by 4 is 100. Yeah, so that's approximately 40. Okay. So that's kind of interesting, 40 degrees Celsius. Because from room temperature to boiling is about 80 degrees Celsius. So if you drop this thing in a vat of boiling water, you should get 2 millimeters increase in length. Okay, so you don't even need flames to get some increases in length there. Okay, room temperature to boiling water. So good, I like that example here. I think we'll leave it at that and get a couple of homework problems for you. Let's see what's good here. We are in chapter 10. Okay, yeah, these are good. So this was the, I have to say one more thing. This was the linear law. So we have for thermal expansion, we have linear, we have area, we have volume. Okay. So we did the linear one. Delta L is alpha L naught delta T. Go ahead and look these up. There's an interesting relation between them. And one of the homework problems I give you is going to require the volume. Okay. The volume law would be delta V is beta V naught delta T. Okay. So beta and alpha won't be the same, but there's an interesting relation between them on solids. Okay, so homework. These are basic, but they're fine. We're looking at chapter 10. And by the way, what is this? Homework number 35. Chapter 10, 1, 7, 12, 13, and 14. 1, 7, 12, 13, and 14. So some of these are the conversions I was talking about to put in your notes. And otherwise, they're just elementary applications of thermal expansion. One of them is interesting because it's the increase in length of a pendulum. So we can talk about that one later as well. It's a good one. Okay, good. See you guys next time.